Okay, so this video is showing you how to do an Arrhenius equation. This is quite a long one, probably one in the exam probably won't be quite as long as this, but the same skills that you need. So they're giving us here a table of temperature going down here and the rate constants here. So we can't plot this, so what we need to plot is 1 over T, but that temperature's got to be in Kelvin first. So the first thing that I've done here is put all these into let's get a different colour. Put all these temperatures into Kelvin, so plus on 273 to each one. Okay, once we've got them into Kelvin, then we convert them into 1 over T, so just do 1 divided by each one. And that gives us the x-axis that we're going to plot. And then over on this side, what can be confusing here is we've got K, the rate constants, and we've got K for Kelvin. So you have to be careful you don't get mixed up here. So we're taking the rate constant K and we're doing the natural log ln of K, and we get these numbers here. Quite often they are negative because the rate constant tends to be a very small number. So this makes our y-axis. So we've got our x and y axis now. So that's the first part done. So, oops. So if we carry on down there, that's worth 5 marks apparently. So we want to plot it now. So I've just made, obviously in the exam you're going to have, they'll probably give you the axes in the exam, or at least part of it, and you'll plot it on there. So I've just done a quick thing here in Excel. So if you look here, these are my 1 over T's again. So you can see they've actually been put in standard form. So that's 3.41 times 10 to the minus 3, 3.36 times 10 to the minus 3, and so on. And here's my natural log of K's, and the graph helpfully has plotted it for me. So this is one bit of the graph. It hasn't got all the way to the y-intercept, but we can see here that it's given us the equation of the graph, and it's given us its line of best fit there. There's a dotted line, and we've got y equals minus 8721.9 x plus 22.979. Okay, so obviously in the exam you wouldn't be given that. You'd have to do a gradient normal way and work it out. So you'd see what dx by dy is. It's normally, well, it is always a negative number, the gradient here. So if you've got a positive number, you've probably done it wrong. Okay, so we're going to take that number then, we're going to use it, that gradient there that we've got from here, the number before the x, that's our gradient, and we can use that. So if I go to back here, so it's to plot the line. I mean, obviously the computer did that for me, but it should always be a line of best fit. It should always be a straight line. So that was my gradient. I just ran into one whole number, and that equals minus EA over R. The gradient always equals this minus EA over R. So basically we're going to times by minus R. So EA equals 8722 times R. R is a constant on your data sheet, 8.314. And that will always give the answer in joules per mole, because R has in its units has joules. So quite often we want it in kilojoules, so we just divide by 1,000 to get it into kilojoules per mole, like so. So that's our activation energy. Remember, activation energy is always positive. You can't get negative activation energy. So now we're looking at how we can use that. So we want to calculate the proportion of molecules of energy greater than the activation energy. We use this little bit of the Arrhenius equation here. We don't need the A part, we just need the exponential factor. So we've worked out EA, we can substitute that in. If you notice there, I've gone back to the joules per mole, because the units have to match what the R is in as well. So you don't put kilojoules per mole there, you always put joules per mole, so watch out for that. You've got R there, and notice there as well, I don't put in 50 degrees, it's got to be in Kelvin, again, so the units match up with R. So we have 323 there. Put that in, and you always get a very silly small number, and that's what fraction of molecules have energy greater than the activation energy in this case.